A plasma globe, such as the one pictured above, is filled with a mixture of noble gases and has a high voltage electrode at its center. Holy mackerel. Does everybody know what an electrode is?
No.
So put it in your notes. Electrode. It is not just a Pokemon character from first gen.
We never heard one?
I actually did not know that. I pulled it up. I'm like, why is this goofy looking character on my Google screen? And I'm like, I read it and it says a first gen Pokemon.
See what it looks like?
It looks like a round thing with eyeballs. Okay. An electrode is a fancied word to describe a conductor leading a current into or out of an object or region. Thank you, parrot. Somebody's parroting me. That's fine. All right. I say again, an electrode is a conductor leading a current, an electrical current, into or out of an object or region. Are you guys familiar with car batteries?
Yeah.
Okay. It's okay if you're not. So a car battery, regular, not an EV. Okay, that's no. They would have these too, but to keep it simple, most of you probably have seen like profile view of a car battery. Looks like a rectangular box, right? And on one end, usually they're out the top. They've got the terminals. They've got a positive terminal and there's a negative terminal. Yes? Sometimes they stick out the sides. Okay? But that's where your cables hook up to the terminal. Okay, guys. A battery terminal is another word for an electrode. Because an electrode is a conductor leading a current, electrical current, into or out of an object. A battery, object or region, the battery, you have the terminals, the electrodes, leading the current into or out of the battery. Does that make sense? Okay, so now you have an example and you understand what an electrode is. Cool. So back to our plasma globe. At the center, there is an electrode. That electrode is leading leading current into that ball. And then it's trying to get out. It's trying to discharge somewhere. So the swirling lines are discharge lines that they're moving. So if this was a moving picture, what do they call it, a GIF? Yeah. Right? You'd see them constantly moving around, trying to find a place to escape out. All right? If you put your hand on that globe, that's where it's going to discharge because you're giving it a better path than just glass insulator. Okay? Moving on to the next section. The electric field. Coulomb's law gives us the formula to calculate the force exerted on a charge by another charge. On some occasions, however, a test charge suffers, I don't like the word suffers there, but it experiences or has exerted upon it an electrical force with no apparent cause. That is, as observers, we cannot see or detect the original charge creating electrical force. All right, stop again. Do we know what a test charge is? No. So, put in our notes. A test charge, in physics, we're talking about a positively charged particle. And think about subatomic particles. Which one's the positive charge? A proton. So we probably have a proton being introduced into the electric field to see how strong the field is, where it's originating at, and we would use Q and sometimes a T, some without, some with a T, as the symbol when we're doing math with it. And that charge, QT or Q, is going to be in coulombs. That unit that we introduced yesterday, a coulomb is equal to an amp times a second. Okay? Everybody remember that from yesterday? Should still be in your notes. How many of you all were absent yesterday? Anybody? Good. So everybody's got that. All right, moving on.
What's the symbol?
QT for charge, test charge. The T is test, Q, for whatever reason, they picked Q for charge. Don't ask me. Okay? All right, here we go. Faraday, this guy Michael Faraday from the 1800s, if I recall properly, dealt with the problem. Is it a funny problem?
Yeah.
Okay, so Faraday dealt with this problem by coming up with this idea of an electric field. We need to define electric field. It is an area around a charged particle. So around a charge, you're going to have an area which will exert a force. In fact, I'll replace the word force here with push or pull. It will exert a push or pull on another charged particle in that area. Or in the field. So an electric field is generated by a charged particle, the area around it, and it will exert a push or pull on another charged particle if it gets in that area or in that field, or close enough to it. And to keep things simple, I'll start off with just a negative particle. That negative charged particle is probably a what? Probably an electron, right? And it's going to create a field around it, an area around it. So we'll just use a circle to kind of show that. And if a charged particle were to get in that field, for example, perhaps a test charge, right? Let's throw a proton in there. It's going to have a push or pull exerted on it by the electric field. Now, wouldn't it also have an electric field that it's generating? Because it's also a charged particle, right? So keep that in mind. But what kind of force would it be, a push or a pull, exerted on that test particle, a test charge?
Pull.
A pull. Why? Because they're opposites, right? So we'd put an arrow there showing that that charge is going toward the source of the electric field. Okay, now as we read, we can refer back to our picture and be like, yep, this is what we mean. Okay, so let's keep reading. According to, before we do, let's look at their definition of electric field and see how close we got. A region of space characterized by the existence of a force that is generated by an electric charge. That's what I said, but in different words, right? All right. According to Faraday, a charge creates an electric field about it, that means around it, in all directions. That's why I used a circle. If a second charge is placed at some point in the field, and the second charge interacts with the field, it experiences electric force. So we placed another charge in here, a test charge, and it is interacting with it in such a way, because it's opposite, it's going to attract. So we have a pulling force. Thus, the interaction we observe is between the test charge and the field, and a second particle at some distance is no longer necessary. I don't know what they mean by that. Anyway, I'm moving on. The strength of the electric field is determined point by point and can only be identified by presence of a test charge. So if you want to know how strong the electric field is over here, you'd have to put the test charge over here. If you want to know how strong the field is over here, you'd have to put the test charge over here. And then you can measure how strong it is and in what direction it is. So if you see this charge move in this direction, you'd know that somewhere over here in this vector, in this direction, you'd have the particle creating the electric field. Does that make sense? Okay. Hopefully. If not yet, we do some math, hopefully it'll make more sense. The field strength can be measured by dividing the force by the charge of the test charge, electric field strength is given the symbol E, and its unit is newtons per coulomb. So here we go. I'm going to rewrite that down here. You do it in your notes too. E equals F on QT. So the force on the test charge divided by the test charge. E is the electrical field strength. In other words, how strong is the electrical field is equal to the force on the test charge divided by the test charge. Now, I'm going kind of fast.
What is QT equal?
It's the test charge. Okay? And we'd be given that most of the time, unless we get really far in. I don't think we get that far into this class. We'll see. What is F?
Force.
That's the force. And what unit do we measure force in? Newtons. Good. So whatever number we have for the force on the test charge, it's going to be in newtons. And whatever our test charge is, the unit that we measure charge in is what? We learned it yesterday.
Amps.
Starts with a C.
Oh,
Coulomb. Yes. So it's going to be newtons per coulomb is how we explain electrical field strength. The newtons, the force exerted on the test charge divided by the test charge. Okay? We're going to do a couple examples. So if it doesn't make sense yet, you'll see how we're given the data. We plug it in the formula to find the field strength. All right, here we go. The test charge can be moved from location to location within the electric field to help map out the whole electric field. So I was saying to find the strength here, you'd have to move the test charge here. If you kept doing that all over within the field, you'd get a map of where the field is and where exactly the charged particle generating the field is. Does that make sense? Yes.
What does the on mean in the equation?
On.
Or
The force exerted on the test charge.
Oh, okay.
Yep, they keep it simple on that one, which is very nice. Okay. So sometimes you'll see this formula just F divided by Q. Okay? They're just giving you a little extra information to make sure you know what they're talking about. Does that make sense? Okay. Here we go. And when you see electric field intensity, intensity is just another word for strength. Okay? So to find electric field intensity, you see it's the same formula, isn't it? Same formula. Okay. Let's watch this guy before we do a couple examples.
Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 27. It's on electric field strength. And before we start talking about that, I'm going to show you a quick simulation. I'm going to add some charges to a box. And the first time I add those charges, I'm going to add 1 coulomb charges. And we're just going to watch their behavior. So each of these particles has a 1 coulomb charge. You can see that they're pushing on each other. Now let's increase the charge to 2 coulombs. And you should be able to realize that...
Do you guys see how they're moving around a little bit more violently, a little more with more energy? Okay? So write this down too. As you increase the charge that's creating the electric field, do you think that electric field will get stronger or weaker? Stronger. If you increase the electric charge that's creating the electric field, you're increasing the strength of that electric field too. And that's very intuitive. It makes easy sense, I think. And I'll try not to he does a good job explaining it. I'll try not to talk too much. Y'all ready? All right, here we go.
There are bigger fields being generated, a greater electric field strength. Now we've got a 3 coulomb charge. They're really pushing on each other. You might have figured out that these are positive charges because the fields are moving away from the charge. And now if we get a 5 coulomb charge, they're really applying a force to each other.
And it's the strongest force that he's showing here. And because they're all positively charged particles, they're all trying to do what with each other? They're They're all trying to repel. They're all trying to get away from each other, and they have a good amount of power or strength to do that. So check it out. There's 5 of the particles in here, and it's in a square box for the simulation. So how many corners are there? 4. So 4 of them are going to end up trapped in a corner because they're all pushing away, trying to get as far away from each other as possible. So 4 of the corners get occupied, and then watch what happens to this poor old 5th.
There's a huge electric field strength, and this one charge can't even find a place to sit.
See how they got pinned in the corners? Because they're all trying to push as far away from each other as possible, and the one's just kind of bouncing around in the middle, trying to find a place to hide.
And so if we take an object, we can measure the electric field strength, and we usually represent that using arrows. And so this object has no charge, but if I add a charge to it, it's going to have an electric field charge, or electric field that's moving out from that positive charge. So if I remove the charge, then I remove that electric field. What's going to happen if I add a negative charge? Well, we're going to have the same size of arrows, but now they're pointed towards the charge.
Towards the charge. All right, so in your notes somewhere, I'm running out of space here. If you have a positive charge, that arrow is going to go away from it. If it's a negative charge, then it'll be towards it. The arrows, by the way, are the electric field lines or vectors. So electric field vectors or lines will be away from positive charges and toward negatively charged particles.
Charge by convention. If I remove the charge, what happens? They go away. Now this video is about electric field strength. And so if I add one charge, get an idea of how long these arrows are, but now let me add one more charge. And what happens is we've increased that electric field strength. And if I add another charge, what happens? Again, we're increasing the electric field strength. It's getting larger. And sometimes it's unwieldy to just increase the size of those. So instead what we'll do is as we add more charges, we just add more arrows. And this will be important when we're looking at, for example, 2 charged plates. And so we could represent the electric field strength as arrows, and as we add charge,
and look, again, you got positive on this side, the arrows go away. On this side it's negative, the arrows go towards the negative.
Increasing the number of those arrows. And so there's a direct relationship between the charge of those plates and the electric field strength. Now it's not always perpendicular, but we're just going to assume that these charged plates are infinitely long. And so in this video, we're really just trying to look at one thing, and that's the relationship between the amount of charge and the electric field strength. And so now I'm going to use a PHET simulation to look at how the...
All right, so we have 4 test charges. So we can imagine these are like 4 protons, and protons have what charge?
Positive.
So the test charge is going to be positive. If he puts a positively charged particle in there to generate an electric field, what are they going to do in relation to that charge? Positives and positives repel. So they're going to try to get away from that charged particle in the middle. If he puts a negative charged particle in here to generate the electric field, then they'll do what? They'll try to go towards that particle.
The amount of charge affects the electric field strength. And we're going to use these electric field strength testers around the outside, and I'm just going to place charges right there in the middle. It's a PHET simulation. I'd encourage you to play around with it. I'll put a link down below. So watch what happens when I add a positive charge in the middle. We've generated an electric field, and as I increase the amount of charge, watch what happens to the electric field strength. It's
The arrows get longer. Also, remember, we got positively charged particles, the arrows away.
There's a direct relationship between the two. And as I pull those charges out, you can see that that electric field strength is going to 0. What happens if we put a negative charge in the middle? You can see that we now have an electric field, but those field lines are pointing towards the charge. As I increase the number of charges, I'm increasing the electric field strength. As I get rid of them, then the electric field strength is going away. But the neat thing about this simulation is you can make it quantitative. So I'm going to add a charge in the middle, and then we're going to turn on the numbers. And you can see that each of these are measuring around 7 volts per meter. Watch what happens as I add a charge in the middle. Now they're all measuring around 14 volts per meter.
Okay, so add more charge, the electric field gets stronger. okay? The volts per meter is a relationship, okay, how many volts, let's, we could actually relate it directly, somebody was asking me if it applies, I think it was you, to the static ball generator that we had out, okay? Are you guys familiar with the term arc or jump? When we're talking about electricity, it can jump. Even if there's a gap between conductors, that electricity can jump. It depends on the voltage. The higher the voltage, the further the distance it can jump. Have you ever heard, usually around storm time, they say stay away from down power lines? Have you heard that before? Usually on the radio or TV, whatever. The reason they're saying that is especially the higher the voltage the power lines carry, the further electricity can jump. So you got a down power line, it's grounded out, well, it can jump to you. Or they'll say, hey, if you're in your car near a down power line, oh, I'm a couple feet away, stay in your daggone car. If you can back away, do so. But if your car is disabled and you're right next to a down power line, a high voltage line, you call for help. Because as soon as you step out, you're outside of your car. Your car acts as something of a Faraday cage. Has anybody ever heard that term before, Faraday cage? All right, put this, can I erase this? Okay, I'll erase up here. Or, no, I'll go over here. A Faraday cage diverts electrical fields around an object that you're trying to protect. So if you want to protect something, put it in a Faraday cage. Your car acts like a Faraday cage. I can't draw very well, so I'm just going to draw a square cage. But if this is fully enclosed, think dog kennel made out of chain link fence. Everybody picture it? A chain link fence, square dog kennel, right? So you have fully enclosed chain link fence. The electric field, no matter how strong it is, it's going to be channeled around to the ground. So whatever is in here, yay me, it protects me from it. Does that make sense? Anybody ever watch, oh, it's a fun show. Have you ever seen Doomsday Preppers? No, it's really fun. The people, like some of them are wild, crazy, whatever, but if they think there's going to be some kind of an EMP, some kind of intense electrical field generated sometimes by the sun, right? They'll say, hey, I'm going to put my sensitive electronics in some sort of a Faraday cage to protect it in case there's a solar storm, real severe, or an EMP, okay? So anyway, your car is a Faraday cage. It's all metal, right? You've got glass insulators, sure, but the electric field will be directed around the car and protect you if you're inside. As soon as you step out, you're not in the cage anymore. That make sense? Stay in your car if you're close to a high voltage line that's down. What?
I don't remember saying yesterday, but what's a coulomb?
A coulomb. Yeah, we just mentioned it again. So 1 coulomb is equal to 1 amp times 1 second of time. So it's how much charge is conveyed across a conductor. If it's 1 amp, 1 ampere, right? That's the flow of electrons, 1 amp, in 1 second of time. It'd be similar to measuring how much water is going through a garden hose in 1 second, right? Total flow. All right? But we're dealing with electricity instead. So that's what a coulomb is. Good question. All right, continuing.
And now let's add one more charge, and what are we going to get? It's going to be around 21 volts per meter. So there's a direct relationship between the amount of charge and the electric field strength. And that's the one thing that you should have picked up. As we add charges, we're going to increase the electric field strength of that electric field.
And you guys already put that down, right? As the charge increases, the field created by the charge gets stronger. Make sense? Good? All right, that's the end of the video. He asked if that helped. I think it did. It helped me for sure. All right, example time. We're going to do a couple examples, and then I'm going to turn you guys loose to finish the lesson, to include the video, and the simulation. I think you guys are going to like the simulation, but don't do what? The 10 questions for points. Do the rest of the lesson except the questions for points. All right, here we go. Got a calculator? If you don't have a calculator, grab one. We're going to This first one here is the example they walk through it. All the math is done for you, but we're going to walk through it so we know how. And then we'll do another one that's not done for us. Hurry up, hurry up, hurry up. All right, here we go. A positive test charge, guys, side conversations, please. A positive test charge. Could you stop flipping around the whatever that is? All right. 2 times 10 to the negative fifth coulombs is placed in an electric field. So we have an electric field generated. We put a test charge in there. The force on the test charge is 0.6 newtons. And you can see, to find the intensity or strength of the electric field, they just plug it into the formula. So go ahead and do that too. Just like that. I know it shows the answer, but go ahead and put it in. I want you to see what it looks like. Because sometimes they'll have their answer in scientific notation, and yours might not be. So we take 0.6 times 2 times 10 to the negative 5, which we need that little caret symbol, right? And then we're going to, did I say times? I did. I did that earlier too. 0.6 divided by 2 times 10 to the negative 5. Hit enter, and we should have 0.000, a bunch of zeros, and a 3. Now I count, correct me if I'm wrong, I count 5 zeros. How many do you have before the 3? I have 0 point, and then I have 5 zeros, and then a 3. What did you guys get? Same? So I think, correct me if I'm wrong, I think we might have found a boo-boo in CK12. Let's check it. So if I have 0.000003, and I want to turn that into scientific notation, they're saying it'd be 4. Well, 1, 2, 3, 4 doesn't get me there, does it?
I don't think so.
I think they're wrong. Unless I'm doing something wrong, you let me know. But I think they're off by a couple. So anyway, you guys get the idea though, right?
Yeah.
So we just plug in our numbers that we're given into the formula. Let's try another one before you guys do the simulation and do the rest of the lesson. All right, we're checking our notes here. The summary, you guys, when you get to the summary, you should be using it to check your notes. Okay, it's a check on your notes. Did I at least get these basics? Now we put extra stuff in there too, like electrode, right? We put extra stuff. And test charge. But we should have at least an electric field surrounds every charge and acts on other charges in the vicinity. Do we have something like that?
Yes.
For electric field, right? The strength of the electric field is given by the symbol E and has the unit of newtons per coulomb. We have that. And then they just repeat it in math form. So we have those. Okay, so we're good on our notes. And let's do this first one. Is weight a force?
Oh, yes.
Yes, because weight is in newtons, right?
Yes.
Force is in newtons, right? Weight is a pull force. Yes?
Yes.
Gravity pulls. Okay. We have weight of a proton, force of a proton, right? 1.64 times 10 to the negative 26. Force goes on the top or the bottom of the fraction? Top. So we're going to take that number and divide it by another number. So put that number in first. 1 point. Times 10 to the negative 26. And we're going to divide that by the charge in coulomb. It says the charge of a proton is 1.6 times 10 to the negative 19. 1.6 times 10 to the negative 19. It says if a proton is placed in a uniform electric field so that the electric force on the proton just balances its weight, what's the magnitude and direction of the field? Well, the force would be up, right? Because it's trying to be pulled down by gravity. So the direction or vector of the force is up. And then the magnitude, we just hit enter now on our calculator. Does everybody already have the number?
Oh, yeah.
is it 1.025 times 10 to the negative 45?
Yes.
No? I hear a bunch of yeses. I've been hearing yeses all day. Check your math. Put it in again. Okay? So show them how to put it in. That's going to be the magnitude of the field strength. At this time, you are released. I think you guys are really going to enjoy the simulation today. It's probably one of the best I've seen. As you know, sometimes I'm disappointed. I'm not disappointed today. What's up? Sure, take a pass.
I got 1.64.
I go and
You didn't type it in right. I showed him.
you didn't even do it.